All tissues in the human body require oxygen to survive. Oxygen is absorbed inside the lungs when red blood cells squeeze by the pulmonary alveoli through small capillaries. Then, red blood cells go on to deliver oxygen to each of the body's tissues. While most tissues can survive without oxygen for fairly long periods of time, the brain malfunctions and becomes injured after just a few minutes. To avoid this potentially catastrophic outcome when breathing ceases, as it happens when people hold their breath underwater, the nervous system deploys a complex strategy to preserve most of the available oxygen for the brain. This strategy is called the dive response. Although the dive response is made up of a combination of several biological effects, it mainly consists of two reflexes: a profound slowing of the heart rate, known as diving bradycardia, and the sequestration of most of the body's blood inside the heart, lungs, and brain, known as the blood shift. When a person's dive response is triggered underwater, it favors the development of a dangerous condition called pulmonary edema. This occurs because air inside the alveoli becomes compressed by hydrostatic pressure, generating a vacuum that suctions fluid from pulmonary capillaries which have become overloaded by the blood shift. This fluid hinders the diffusion of oxygen towards the red blood cells, causing brain hypoxia, loss of consciousness, and in the worst cases, death. Some convulsive seizures also cause death. While it is not known why this happens, these lethal convulsions are typically preceded by a prolonged cessation of breathing, severe bradycardia, and pulmonary edema. As these pathological events are strikingly similar to the events that precede pulmonary edema underwater, we have hypothesized that seizure-induced deaths are caused by augmented forms of the dive response.